Hi, so today we're going to discuss the magnetic field, motion of a charged particle in a uniform magnetic field, applications of charged particles moving in a magnetic field, the magnetic force on a current carrying conductor, the torque on a current loop in a uniform magnetic field, the Biot-Savart law, the magnetic force between two parallel conductors, Ampere's law, and magnetism in matter. We will now discuss the magnetic field. So, in discussing magnetism, we will see that it is strongly related to to electricity, okay, and cannot be separated from it. So, for example, moving electric charges produce magnetic fields, and magnetic fields affect moving charges. And the union between electricity and magnetism is known as the field of electromagnetism. Okay, so magnetic fields can be found in the region of space surrounding a moving charge. Okay, and it can also be found in and around materials that have permanent magnetism, such as this magnetic bar. And the magnetic field is a vector quantity, so this B, and this direction can be found using a compass where the direction of the north pole of the compass is the direction of the magnetic field. Okay, so as you can see in this example of a bar magnet, it shows the magnetic field revealed by using compasses. And as you can see, the magnetic field forms magnetic field lines similar to those we have seen for the electric field, right? And one way one way you can use to reveal the magnetic field is to place small iron fillings in the vicinity of the bar magnet, like in this picture here, and the iron fillings will form patterns that will reveal the magnetic field. So, in the same way, we can detect the existence of an electric field by placing a test charge at a certain point. The existence of the magnetic field at a certain point can be found by measuring the magnetic force Fb experienced by a test charge placed at that point. Okay. So, experimental results show that the magnetic force on a charged particle is of this form. So, Fb is equal to QV cross B. So, it's the vector cross product, and Q is the charge of the particle, and V is its velocity. And so, this shows that the direction of the magnetic force is perpendicular to the plane formed by V and B. Okay, so this is the plane formed by V and B. It's perpendicular to the plane, and you can use the right hand rule to find its direction. So if you curl your fingers from V to B, the direction of FB is in the direction of your thumb, okay, if Q is positive. And if Q is negative, the direction of FB is in the opposite direction. So if you use the right hand rule here, you curl, so this is a negative charge moving in a magnetic field. So if you curl V towards B, because it's negative, the direction of FB is in the opposite direction, okay? And so the units, the SI units of the magnetic field is the Tesla, and you can using this equation, 1 Tesla is equal to 1 Newton times second per Coulomb times meter. And the magnitude of the magnetic force is given by QVB sine theta, and theta is the angle between V and B. So as you can see here, FB is 0 if V is either parallel or anti-parallel to B, so if the angle is either 0 or 180 degrees, right? And FB is maximum if V is perpendicular to B, so the angle between them is 90, as in this case here, right? Then FB max is equal to QVB. And so this equation for the magnetic force shows that unlike the electric force, which we have seen before is in the same direction as the electric field, the magnetic force vector Fb is perpendicular to the magnetic field. Okay. So this is one difference from the electric force. Another difference is that the electric force acts on a stationary or a moving charged particle, right? But as you can see from this equation, the magnetic force acts on a charged particle only if it's moving, because if V is equal to 0, there is no magnetic force, okay? Um, so, um, Also, another difference is that the electric force does work on the charged particle as it is displaced. So, the electric force will, when it acts on a charged particle, the particle will gain kinetic energy because the electric force is doing work on it, right? But the magnetic force does no work as the particle is displaced, right? And this is because if a charge moves in a constant magnetic field, the magnetic force is always perpendicular to the displacement. So for an infinitesimal displacement, ds here, the work done by the magnetic force, dw, is equal to fb dot ds is equal to fb dot v dt is equal to 0, and this is because fb is perpendicular to v, right? And so it follows from the work energy theorem that the kinetic energy of a charged particle does not change due to a magnetic field. The magnetic field can only change the direction of the velocity of the particle, but not its speed. So it will change when it acts on a particle moving, the direction of the particle will change, but not the magnitude of the velocity, not the speed. So um, also, a note here about how to represent the direction of the magnetic field in a like this plane. So we use dots to represent magnetic field vectors going out of the page, and we use crosses to represent magnetic field vectors going into the page, okay? So we will now consider the motion of a charged particle in a uniform magnetic field. So suppose we have a positively charged particle moving in a uniform magnetic field with an initial velocity vector that is at an angle of 90 degrees to the field. So the velocity vector is perpendicular to the field, okay, as you can see here. The field is into the page. So in this case, the magnetic force will be directed in this direction. It's a centripetal force, and it will cause the charge to change its direction. And as the charge will change its velocity direction, the magnetic force will continue to be perpendicular to the velocity, and so the particle will follow a circular path, and the motion is a uniform circular motion because the velocity vector is only changing its direction, but its magnitude will remain constant, right? So since the charge is positive, the rotation is counterclockwise. If the charge is negative, the magnetic force will be in the opposite direction and the rotation will be clockwise. And so the net force on the particle is equal to Fb equal to ma, and a is the centripetal acceleration given by v squared over r. The magnetic force is qvb, and from this we get the radius of the circular path of the particle in this magnetic field is equal to mv over qb. And so as you can see, the larger the linear momentum mv of the particle, the larger the radius of the path will be, right? And also, the larger the charge of the particle or the magnetic field, the less the radius. So let's say, for example, we have a proton moving in a circular orbit with a certain speed in a uniform magnetic field. Then it will have a certain radius of orbit, rp, right? If an electron moves with the same speed of the proton in the same magnetic field, So everything is the same except that the mass of the electron is much smaller than the proton, and we know that the charge of the electron is the same as the proton. So the radius of the path of the electron is equal to me over mp rp, okay? And this shows that the radius of the path of the electron is smaller than that of the proton, okay, because it has less mass, and so the magnetic force will be more able to bend the electron into the circular path than that of a proton. So the angular speed of the particle is given by this equation: V over R is equal to QB over M, and is often referred to as the cyclotron frequency because it is the angular speed in a type of accelerator known as the cyclotron, okay? The period of motion, which is the time required for the particle to complete one revolution, is given by 2 pi r, the circumference, over v, which is equal to 2 pi over omega, so 2 pi m over qb. Okay, and now suppose the initial velocity of the particle is not perpendicular to the magnetic field but is at some angle to it, then the path of the particle will be a helix, as you can see in the figure here, okay? So we will now consider applications of charged particles moving in a magnetic field. So suppose a charged particle is moving with a velocity v and is subjected to both an electric field E and a magnetic field B at the same time. It will then experience both an electric force QE and a magnetic force QV cross B, and the total force known as the Lorentz force is given by this equation, okay? So the first application of charged particles subjected to the Lorentz force is the velocity selector, shown in this figure. So in many experiments, it is important to have all particles moving with the same velocity, right? And this can be achieved using the arrangement shown in this figure, where a region of space contains an electric field directed to the right here. Okay, so in this region of space, the electric field E is directed from the positive to the negative plate, and the magnetic field is directed perpendicular to the electric field and into the page. This is the magnetic field is directed into the page and is perpendicular to the electric field, okay? So suppose a positive charge with a velocity v directed upwards enters this region, then the magnetic force qv cross b, which is Fb here, is directed to the left, and the electric force qe, which is Fe, is directed to the right. So if the magnitudes of the fields E and B are chosen such that QE is equal to QVB, then the particle won't feel any force because the net force on it is zero, and it will continue its straight line motion through the region containing the fields without being deflected, right? So from the expression here, you can see that only those particles with a speed of E with a speed equal to E over B will be able to pass through the fields without being deflected. If the speed of the particle is greater than this value, the magnetic force will be larger than the electric force and the particle will be deflected to the left. And if the speed is lower than this value, the electric force will be larger than the magnetic force and the particle will be deflected to the right. So another application of the Lorentz force that we will consider is the mass spectrometer, which is a device used to separate ions according to their mass to charge ratio. So first, a beam of ions pass through a velocity selector, and then they enter a second region here, where with a magnetic field B naught that has a different value than the magnetic field of the velocity selector, but has the same direction. And then, so here they bend and follow a semicircle of radius r before they strike a detector here. And the beam deflects to the left if the ions are positively charged, and it deflects to the right if the ions are negatively charged. And using the equation for the radius of the path, which is equal to mv over q b naught, we get for the mass to charge ratio, m over q is equal to r b naught over v. And if we substitute for v as e over b, since only ions with this velocity will be able to pass through and get to the second region, we get this expression for the mass to charge ratio. So if we know B naught, B and E, we can find the ratio M over Q. So the physicist Thomson has used this technique and apparatus here to measure the ratio M over Q for an electron. First, electrons are accelerated from the cathode and pass through two slits, and then they enter a region containing perpendicular electric and magnetic fields. So these two plates here produce an electric field, and this is a magnetic field produced by coils here and here. First, the magnitudes of the two fields are adjusted as to produce an undeflected beam like this one. And if the magnetic field is turned off, the electrons are deflected from the straight line, like here, due to the electric field. And they strike a fluorescent screen, okay? So measuring the deflection of the beam and using the values of E and B, one can find the charge to mass ratio. So a third application of the Lorentz force that we will consider is the cyclotron, which is a device that can accelerate charged particles to very high speeds. And then these particles are used to bombard other particles like atomic nuclei. Okay, so as you can see here, the charged particles move inside two hollow metal containers of semicircular shape, named D1 and D2, because they are shaped as the letter D. Okay, a high frequency alternating potential difference is applied to the Ds, and a uniform magnetic field is applied perpendicular to them. A positive ion is released here at the center, then it will move in a semicircular path in one of the Ds due to the magnetic field, okay? So it moves in a semicircle and then it arrives here at the gap after a time of t over 2, where t is the time for one complete trip around the D. So the frequency of the applied alternating potential difference is made as to match the time needed for the ions to travel through 1D. So this frequency of the applied potential represents the frequency at which the polarity of the Ds is reversed, right? So if the potential difference between the two Ds is delta V, then as the ion crosses the gap, it will accelerate and gain kinetic energy equal to Q delta V, okay? And each time this happens, its speed will increase and it will move in a semicircular path of a larger radius because the radius is proportional to the momentum of the particle, okay? So after a time of t over 2, it again arrives at the gap, okay? So it will again arrive at the gap, and because the polarity is reversed after that time, the ion will receive another kick and it will accelerate again, increasing its speed further. So this continues and the ion gains an additional energy of Q delta V for each half circular trip, okay? So when the radius of the circular path is nearly equal to that of the Ds, the high-speed ions leave the system here through an exit slit, okay? So if R is the radius of the Ds, then using V equal to QBR over M, the kinetic energy of the ion when it exits from the cyclotron will be given by this equation. Okay, so note also that if the energy of the ions in the cyclotron exceeds about 20 mega electron volt, then relativistic effects become significant, and the ion's motion does not remain in phase with the applied potential. In some accelerators, this problem is solved by modifying the frequency of the applied potential so that it will remain in phase with the motion of the ions. So we will now discuss the magnetic force on a current-carrying conductor. So as we have seen previously, a single charged particle, when moving through an external magnetic field, will experience a magnetic force, right? And because a current-carrying wire is a collection of many charged particles in motion, then it follows that it will experience a magnetic force when placed in an external magnetic field, right? Because the magnetic force is the resultant of the sum of the individual magnetic forces on the moving charged particles in the wire, okay? So each charged particle moving, making up the current, will experience a magnetic force, and the sum of all will give the resultant magnetic force on the wire. So this figure here shows a wire placed in a magnetic field directed into the page. So if a current is set in the wire will deflect to the left if the current is directed upwards, and to the right if the current is directed downwards. So consider a segment of wire of length L and a cross-sectional area of A carrying a current I and placed in a uniform external magnetic field B. For the charged particles in motion, we shall ignore the zigzag motion we have discussed previously, since the net velocity of this motion is zero, okay? And we will only consider the drift velocity. So for a charged particle moving with a drift velocity Vd in an external magnetic field B, the magnetic force is given by QVd cross B, okay? So this is for just one charge carrier. The total magnetic force on the wire segment is the magnetic force on one charge multiplied by the number of charges in the segment, right? The number of charges in the segment is given by NAL, where AL is the volume of the segment, okay? And N here is the number of charges per unit volume, okay? So the total magnetic force on the wire of length L, FB, is equal to QVD cross B times NAL. So since the current is given by NQVDA, so we may write FB equal to IL cross B. And L here is a vector in the direction of I, and its magnitude is equal to the length of the segment, okay? So note here that this expression applies only to a straight segment in a uniform external magnetic field, okay? But for an arbitrary shaped wire of a uniform cross-section, as you can see here, that is placed in an external magnetic field, the magnetic force on an infinitesimal segment of length ds here is given by this equation. So dFB is equal to I ds cross B, and ds here is a vector for the infinitesimal length segment, okay, and its direction is the same as that of the current. And df in this case is directed here out of the page. So this shows that the force on the wire element df is maximum if B is perpendicular to the element, right? And is zero if B is parallel to the element. So the total magnetic force Fb on the wire between 2 points A and B is equal to I integration of A to B ds cross B. So we will now consider the force on a semicircular conducting wire of radius r forming a closed circuit and carrying a current I. So suppose a uniform magnetic field is directed along the y-axis, okay? And we want to find the magnetic force on the straight portion of the wire and on the curved portion. So for the straight portion, we have Fs equal to I integration from A to B ds cross B, which is integration from minus R to R, B dx K. K because Fs here is directed in the Z direction, okay? And this is equal to 2I R B K, okay? So for the curved portion, dfc is equal to I ds cross B, which is equal to minus IB. So if you use the right hand rule for ds cross B, it will be in the negative K, in the negative Z direction. So minus IB sine theta ds K. The angle between ds and B is theta, right? And also we know that ds is equal to r d theta, okay? And so Fc is equal to minus the integration from theta is equal to 0 to 180 degrees of IRB sine theta d theta k. And IRB are constants, so they go out of the integration. And if we integrate, we get Fc is equal to minus 2 IRBk. So as you can see, the magnitude of the magnetic force on the curved wire Fc is equal to that on the straight wire Fs between the same 2 points where both carry the same current. So this shows that the net magnetic force on any closed loop in a uniform magnetic field is 0. So Fs plus Fc is equal to so we will now discuss the torque on a current loop in a uniform magnetic field. And we shall show that even though the net force on the current loop in a uniform magnetic field is 0, the net torque is not 0. And this is the basis for the operation of motors and generators because the loop will start to rotate. So let's consider a rectangular loop carrying a current I and placed in a uniform external magnetic field B directed to the right in the plane of the loop. So the magnetic force on sides 3 and 4 is 0 because the wires are parallel to the field, okay? But for sides 1 and 2, because the wires are perpendicular to the field, we have the force on the force on side 1 is equal to that on side 2 in magnitude is equal to IAB. And the direction of F1 is out of the screen and F2 is into the screen, okay? And here in this figure, it shows a view of the loop if you look from side 4, okay? So if the loop is pivoted so that it can rotate about an axis that is passing through O and perpendicular to the screen, then the two forces F1 and F2 will produce a net torque about this axis, okay, and the loop will rotate clockwise when we view the loop from side 4. Magnitude of the torque is given by tau max is equal to F1 B over 2 plus F2 B over 2. And if we substitute for F1 and F2, we get the torque is equal to I AB B, and AB is the area of the loop, okay? And if the current is reversed, the rotation will be counterclockwise, okay, if we view from side 4. So now suppose the plane of the loop is not parallel to B, but at some angle to it, as in here, in this case. Or we can say that a line here, perpendicular to the plane of the loop, makes an angle theta to B. So notice that B here is still perpendicular to sides 1 and 2. And the magnetic forces on the sides 3 and 4 cancel each other out and produce no torque because they have the same line of action, okay? So The magnetic forces on the sides 1 and 2 produce a torque about an axis passing through the center of the loop, and the moment arm of each force, F1 and F2, is equal to B over 2 sine theta. So this is the moment arm. And so the net torque is given by this equation. So tau is equal to B sine theta, and this is the area. So tau is equal to I A cross B. And this is why we call this tau max, because the angle between A and B is 90 degrees here, in this case, okay? So, uh, which, uh, uh, which represents the maximum torque. So, is maximum when B is parallel to the plane of the loop, and the angle between A and B is 90 degrees, and the torque is zero if B is perpendicular to the plane of the loop, and the angle between A and B is equal to zero. Okay, so A is a vector perpendicular to the plane of the loop and has a magnitude equal to the area of the loop, okay? And its sense can be found using the right hand rule by curling the four fingers of the right hand in the direction of the current. Okay, so if we curl four fingers in the direction of the current, we get A out of the page here, okay? So the thumb will point in the direction of vector A. So note that the loop tends to rotate in the direction of decreasing values of theta towards A being aligned to B. Okay, so it tends to go to the state of A being aligned to B. And the magnetic dipole moment mu of the loop is defined by this equation. So mu is equal to IA. Okay. So the SI units of the magnetic dipole moment is ampere times meter square. And so we can write the torque as mu cross B. Okay. And this expression is valid for any loop of any shape, not necessarily rectangular. Okay. So for a coil consisting of multiple loops with n turns, each carrying the same current and of the same area, the total magnetic moment of the coil is the product of the number of turns n and the moment the magnetic moment for each loop in the coil, which is IA. So mu is equal to NIA, okay? And so the torque on a coil of n turns is n times greater than the torque on one turn in the coil, okay? So now suppose that this loop, which is initially making an angle theta to the magnetic field, is released from rest. Then the magnetic moment vector, which has the same direction of A perpendicular to the loop, will begin to rotate clockwise as to line up with the field, okay? So when mu rotates towards B and once mu become aligned to B, it will represent the equilibrium position of the loop, but the angular momentum of the loop will carry it past this equilibrium configuration, where it will slow down due to the restoring torque, okay? And so the resulting motion will be an oscillation around the equilibrium position where mu is aligned to B. So before the loop was released from rest, the energy was in the form of potential energy of the loop field system and is given by this equation, U is equal to minus mu dot B. So U has a minimum value when mu is parallel to B and is equal to minus mu B, and it has a maximum value when mu is in the opposite direction of B and it will be equal to plus mu B, okay? And so we can summarize the previous discussion that a moving charge placed in a magnetic field experiences a magnetic force, and a current carrying wire placed in a magnetic field also experiences a magnetic force, and a current carrying loop placed in the field experiences a torque. So we will now discuss the sources of magnetic fields. So in 1819, Ørsted has found that a compass needle placed near a current-carrying wire is deflected which indicates that the current in the wire is the source of a magnetic field, okay? So in the early 19th century, the physicists Biot and Savart derived an expression for the magnetic field at a point in space due to a current producing the field based on experimental results, okay? So suppose we have a wire carrying a current I, as shown in the figure here. Then the magnetic field dB at a point P due to an element of infinitesimal length ds is given by this equation. And this expression shows that dB at a point is perpendicular to both ds and r, okay? This is the unit vector r. And it also shows that the magnitude of dB is inversely proportional to r squared, where r is the distance from the point P to the element of the wire. And also, the magnitude of dB is proportional to the current I and to the length of the element ds, and also to the sine theta, where theta is the angle between r and ds. Km is a constant equal to 10 to the minus 7 Tesla times meter over Ampere, and it usually is written as mu naught over 4 pi, where mu naught is the permeability of free space, okay? So we will now consider the example of using the Biot-Savart law to find the magnetic field of a circular current loop. So consider a loop of radius A that is in the YZ plane and carrying a steady current I. We want to calculate the magnetic field at a point here P along the x-axis that passes through the center of the loop, okay? The magnetic field dB due to a current element ds is shown here. This magnetic field dB can be resolved to two components, dBx and dB perpendicular, okay? So for a current element also at the bottom, due to symmetry, the perpendicular component dB perpendicular will be in the opposite direction, and it will cancel out with the component for the top element, okay? And this is true for all elements around the ring. So all of the opposite pairs will have their perpendicular components cancelled out with each other, and only the parallel component dBx for all the elements will add up. So you can see from here that ds is perpendicular to the unit vector r, and so ds cross r is equal to ds times 1 times sine 90, which is equal to ds. And so dB is equal to mu naught I, absolute value of ds cross r over 4 pi r square. This is equal to ds, and r square is equal to a square plus x square. And the x component of dB is equal to dB times cosine theta, and cosine theta is equal to a over r, and r is equal to the square root of a square plus x square, okay? And the total magnetic field at P is equal to the, due to the whole loop, is equal to the closed integral of dBx, and these are constants for the elements, and so we have the integration of ds. This goes out of the integral, and the integration of ds is 2 pi a, the circumference of the loop, and this gives this expression for bx, okay? So at the center of the loop, for x is equal to 0, if we substitute, we get bx is equal to mu naught I over 2a, okay? So the magnetic field lines for a circular loop is shown here, where only the lines in the plane containing the axis of the loop are shown, okay? The field line pattern of this loop is similar to that of a bar magnet, right? From this expression here, if we want to find the magnetic field at points far away from the loop, so at x much larger than a, we can ignore a, and we get in this here at this bracket, and we get bx is equal to mu naught I a square over 2x cube, and we know that mu, the magnetic moment of the loop, is equal to I pi a square. So we substitute here, so mu naught mu over 2 pi x cube. And this expression is similar to that of the electric field of an electric dipole, okay, where E is equal to KEP over y cubed at points far away from the dipole, and the magnetic moment, the electric dipole moment is equal to 2a cube. So we will now discuss the magnetic force between two parallel conductors. So we have previously showed how a current-carrying conductor, like a straight wire placed in an external magnetic field, experiences a magnetic force, right? And we have also showed that a current-carrying conductor has its own magnetic field, okay? And so if we place two wires, each carrying current I1 and I2 next to each other, each will exert a magnetic force on the other, okay? So let's consider two long straight parallel wires separated by a distance a and carrying I1 and I2 in the same direction. We shall assume a simplified model here in which the radii of the wires are much smaller than the distance between them. So wire 2, which carries the current I2, set up a magnetic field around it, okay? And let's consider this magnetic field to be B2 at the position of wire 1, as you can see here, okay? And you can see that B2 is perpendicular to the wire 1, okay? And so the force on wire 1 due to the field of 2 is given by this equation. It is actually I1 L cross B2, but since L and B2 are perpendicular, we may write it, the magnitude of F1 is equal to I1L B2, okay? And the B2 is given by this equation. It's mu naught I2 over 2 pi A, okay? And so we have F1 is equal to mu naught I1 I2 over 2 pi A L. And so the force per unit length on wire 1 due to the field of 2 is equal to F1 over L, which is equal to mu naught I1 I2 over 2 pi A. And the direction of F1 is downwards towards wire 2, and you can find this from the right-hand rule if you curl your fingers from L towards B2. And following similar analysis, the force F2 on wire 2 due to the field of wire 1 is equal in magnitude to F1 and is opposite in direction. So it is directed upwards towards wire 1, okay? And this also follows from Newton's third law. So the magnetic force per unit length exerted by each long current carrying wire on the other is given by F over L, okay? Equal to mu naught I1, I2 over 2 pi A. And this equation also applies if one wire is of infinite length and the other is of a finite length. And so if the currents are in the same direction, the parallel conductors will attract each other, and if the currents are in opposite directions, the parallel conductors will repel each other, okay? And the useful application of this force is that it can be used to define the unit of Ampere. So if we have two long parallel wires that are 1 meter apart, so A is equal to 1 meter, and each is carrying the same current, and the force between the force per unit length on each wire is 2 times 10 to the minus 7 Newton per meter, then the current in each wire is equal to 1 ampere, okay? So we will now discuss Ampere's law. So in previous videos, we discussed Gauss's law, which describes the relationship between an electric charge and the electric field it produces. And we have shown that Gauss's law can be used in highly symmetric charge distributions. Okay? So Ampere's law is an analogous relationship in magnetism between a current and the magnetic field it produces. And it can also be used in highly symmetric current distributions. Okay? So for the wire shown here, as we have seen in previous slides, the lines of the magnetic field form circles around the wire. And if we take a path around the wire and we evaluate the closed integral of B dot ds, you can see that B is parallel to ds, so the dot product is equal to B ds. And so by symmetry, B is constant in magnitude around the circle because all points on the circle are at the same distance from the wire, okay? And so the sum of B ds over the closed path is given by this equation. So the closed integral of ds is equal to 2 pi r, and 2 pi r is the circumference of the circle. So note that even though we derive this expression for a circular path, it applies in the general case of a steady current passing through an area surrounding an arbitrary closed path, okay? So Ampere's law states that the line integral of B dot ds here around any closed path is equal to mu naught I, and I is the total steady current that passes through any surface bounded by the closed path. So similar to the conditions we stated previously on how to choose a Gaussian surface, when choosing the path of integration in Ampere's law, also known as the Amperian loop, we need to consider the following conditions. So first, the magnitude of B to be constant over the path. Second, B and ds either parallel or perpendicular. And third, that B is 0 over the path, okay? So as an example of Ampere's law, let's consider three paths here, A1, B, and C. And we want to rank the magnitude of B dot ds for the three paths from greatest to least. So the direction of the current here is out of the page, and here is into the page, and this is out of the page. So the magnitude of the integration of B dot ds is greatest for the path A, right? Because it's 7 minus 2 equal to 5. Then C, which is 4, so 6 minus 2. And then B, okay, which is 1. So we will now discuss the magnetic field of a long current carrying wire. So consider a long straight wire of radius r carrying a current I that is uniformly distributed over the cross-section of the wire, and we want to calculate the magnetic field at a distance r from the center of the wire. Okay, so for this path 1 here, we have this integration. So B is from symmetry, B is constant in magnitude along path 1, and this direction is parallel to ds, okay, at every point of the path. So this is using Ampere's law. We get B is equal to mu naught I over 2 pi r for r greater than or equal to 1. And I here is the total current in the wire, since all of it passes through the path 1. But for the interior of the wire, which is, if we take here path 2, the current passing through the plane of path 2 is not the total current, but is I dash. And I dash over I, the ratio is given by the area of path 2 over the cross section of the wire. Okay. We substitute this expression for I dash into Ampere's law, and we will get this expression here. Okay. So this figure here shows a plot of B versus R. So first, as you can see, from the center to the radius of to here, the radius of the wire, it is linear relationship. So B is proportional to R. Then here, at distance larger than R, it's proportional to 1 over R. Okay. And so you see, for highly symmetric current distributions, it is much easier to use Ampere's law than Biot-Savart law, right? Okay, and so also note that as we go to 0, as R goes to 0 here, B will also go to 0. Okay, and also the two expressions here, this one and this, will give the same value for the magnetic field if R is equal to the radius of the wire, okay? And this shows that the magnetic field is continuous at the surface of the wire. We will now discuss the magnetic field created by a toroid. So the toroid is a useful device to create a uniform magnetic field, and it consists of a conducting wire wrapped around a ring of a non-conducting material. Okay, so suppose there are n closely spaced turns, and we want to calculate the magnetic field in the region occupied by the ring at distance r from the center. And the torus could be air, so the toroid could be just a wire wrapped into the shape shown here, okay? So we can use Ampere's law because a toroid has a high degree of symmetry. So by symmetry, the magnitude of B is constant around this path 1, and its magnitude is parallel to ds, tangent to the path, which means that B dot ds is equal to B ds, so B is constant, it goes out of the integral. And also, since the wire is wrapped n times, and since the current in each loop is I, so the total current passing through a surface bound by this path 1 is equal to Ni. Okay? So applying Ampere's law, we get this equation. So the integration of ds is the circumference of the path, which is equal to mu naught. So B 2 pi r is equal to mu naught Ni. And this is the expression for B. And this shows that B varies with 1 over R, okay, and therefore it's non-uniform inside this torus. But if R is very large compared to A, which is the cross-section of the torus, then the field is approximately uniform inside the torus, okay? Also, for an ideal toroid in which the turns are closely spaced, the external magnetic field outside the torus can be approximately to be 0. So if path 1 is taken such that R is either smaller than B or larger than C, in both cases the path encloses 0 net current, so that the closed integration of B dot ds is equal to 0. But still, this does not mean that B is equal to 0, because in this case, the integration of B dot ds is equal to 0 because the field lines are perpendicular to ds in these if R is less than B or greater than C, and not because B is equal to 0, okay? And if we consider path 2, there is a net current passing through path 2, which produces a weak magnetic field in the regions external to the toroid. So another configuration that can produce a uniform magnetic field is a solenoid, which consists of a long wire wrapped in the form of a helix, and the turns are closely spaced. So this is a helix. The wire is wrapped like that, okay? So each turn represents a current loop, okay? And the net magnetic field is the vector sum of the fields due to all of these turns. For closely spaced turns of a solenoid of finite length, the field lines are shown here, and they diverge from one end and converge in the other, similar to the field lines of a bar magnet, where one end of the solenoid behaves as like the north pole of a bar magnet and the other end as a south pole, okay? And the field inside the solenoid becomes more uniform as its length increases. So the field becomes more uniform inside. And an ideal solenoid is one in which the turns are closely spaced and its length is really large compared to its radius. Uh, Also, for an ideal solenoid, the field outside is approximately zero and the field inside is uniform, okay? So let's consider path 1, which is a rectangular loop of length L and width W. And we see that the dot product of B dot ds is 0 along the side 3 here because the magnetic field lines are perpendicular to the path. And also for sides 2 and 4, the dot product of B dot ds is also 0 because B is also perpendicular to ds, both inside and outside of the solenoid. And for side 1, we have this integral. So the closed integral for path 1 is equal to the integral only for side 1, b dot ds, which is b integration of ds bl, and for path 1, this whole rectangle, the total current passing through is Ni. So BL is equal to mu naught Ni, and this gives us this expression. So B is equal to mu naught Ni, and N, which is equal to N over L, is the number of turns per unit length. And this equation is valid only for points near the center of the long solenoid. The field near the ends is smaller than the value given by this equation, okay? Also, if you consider path 2, it encloses a small current producing a weak magnetic field external to the solenoid. So we will now discuss magnetism in matter briefly, but we will go into more details in other videos. So let's consider Bohr model of the atom shown here, where electrons are assumed to be moving in circular orbits about the more massive nucleus. Okay, so each orbiting electron can be considered as a tiny current carrying loop. And the current is equal to E over T, and E is equal to 1.6 times 10 to the minus 19 coulomb. According to Bohr's model, the electron circles the nucleus once every 10 to the minus 16 seconds, and this gives a current of 1.6 times 10 to the minus 3 ampere. And this figure shows the angular momentum associated with the electron and the magnetic moment mu. So because the electron has a negative charge, the direction of mu is in the opposite direction to the angular momentum. So the current produced by the orbiting electron is I is equal to E over T equal to E omega over 2 pi, which is equal to EV over 2 pi r. The magnetic moment of this current loop is IA, which is equal to the current times the area of the circle, which is equal to half EVR, okay? And since the angular momentum of the electron is given by mvr, then we may express the magnetic moment in terms of L equal to E over 2 pi r L, okay? And note that both the vectors mu and L are perpendicular to the plane of the orbit. And we shall see in later videos of quantum mechanics that the orbital angular momentum of the electron is quantized and is an integer multiple of h bar, okay? H bar is equal to h over 2 pi, which is equal to 1.06 times 10 to the minus 34 joule times seconds. So h is the Planck's constant. And so L is equal to 0 h bar, 2 h bar, 3 h bar, and so on. Therefore, the smallest non-zero value of the magnetic moment, mu, is equal to E over 2 pi r h. Okay. So in most materials, the magnetic moment of one electron in an atom is cancelled out by that of another electron rotating in the opposite direction. And so the net magnetic effect produced by the orbital motion of the electrons is either zero or negligible, but in some substances, these contributions from orbiting electrons will add up and will produce a net magnetic effect. So in addition to the orbital angular momentum, the electron also has an intrinsic magnetic moment called spin. And other particles like protons and neutrons also have spin, okay? And the spin can be approximately modeled as due to rotating charges. But we will discuss it in more details together with the orbital angular momentum in later videos of quantum mechanics, okay? So as we said, the electron can be viewed as a charged sphere spinning about its axis. At the same time, it is orbiting the nucleus. But this classical description is just to help visualize it. But the spin of the electron actually arises from relativistic dynamics, which are incorporated into quantum mechanics, okay? And we will get to this in other videos. So using the quantum theory, the magnitude of the spin angular momentum is given by h bar over 2, which is 5.27 times 10 to the minus 35 joules times seconds. And the intrinsic magnetic moment associated with the spin of an electron has this value, E over 2m h bar, equal to 9.27 times 10 to the minus 24 joule per Tesla. Which is of the same order of magnitude as the magnetic moment of the smallest non-zero value of the orbital motion, right? And this quantity is known as the Bohr magneton. So in atoms or ions, the electrons usually pair up with spins being opposite to each other. Okay, and this results in the cancellation of the spin magnetic moment. But atoms that contain an odd number of electrons have at least one electron that is unpaired, okay? So it's not cancelled out by another spin in the opposite direction. And therefore, this atom will have a net spin magnetic moment, okay? So the total magnetic moment of an atom is the vector sum of the orbital and spin magnetic moments. And the nucleus of the atom also has a magnetic moment that is associated with the protons and neutrons. But this magnetic moment is small compared to that of the electron by a factor of approximately 10 to the power 3, and this is due to the larger masses of the proton and neutron, and therefore it can be neglected. And we will discuss the magnetization of materials in details in other. So in the following slides, I included some solved examples. Thank you for watching. Please don't forget to like and subscribe, and see you in the next video.